What's happening, y'all? Welcome back. In this video, we're going to continue our conversation about introductory eigenvalue theory. Specifically, recall that when we're studying the problem ax equal lambda x, we call that the standard eigenvalue problem. We introduced this analogy in the last video that we can think about the story of eigenvalue education like the story of human mobility. In this video, we're going to further refine our different steps of eigenvalue education into introductory and advanced steps and give an overview of the specific focus we're going to make at each stage in our introduction to eigenvalue theory. Recall from the last video, we said that there were really 8 steps in our process of becoming experts in eigenvalue theory, the first 4 of which were going to be the focus of the introductory explorations that we do in this course. With that in mind, we've already become aware of an eigenvalue problem via the study of the couple pendula problem that we did in the first eigenvalue lesson. From here, the rest of this lesson is going to be focused on solving small problems using pen and paper analysis by hand. We're going to start with an overview looking at case studies of eigenvalues of 2 by 2 matrices. We're going to get a really good idea of the different types of eigenvalues and eigenvector pairs that show up in the 2 by 2 case. We're going to then leverage that information to study the 3 by 3 case and get some ideas of the type of eigenvalues and eigenvectors that show up in that situation. Given the insights that we build in both 2 by 2 and 3 by 3 matrices, we're then going to generalize to a study of what we call the characteristic equation as well as properties of the characteristic polynomial. Once we've built meaningful intuition using examples in small problems about the type of eigenvalue and eigenvector pairs that show up, and we've started to think about characteristic polynomials and how to solve that, we are then going to leverage that intuition to build basic eigenvalue theory. The start of that process is going to be to focus on diagonalization. How do we diagonalize a matrix given that we have a full eigenvalue basis? The next thing we're going to talk about is the concept of similarity transformations. Similarity transformations actually set the foundation for computational algorithms in eigenvalue theory. That's a very powerful strategy that is involved in intermediate and expert level eigenvalue calculations. We're then going to look at eigenvalue and eigenvector theory for specialized algebraic structures. Specifically, we're going to take a look at what happens when we're trying to find eigenvalues of symmetric matrices. That will lead to the discussion of an even more specialized group of matrices called positive definite matrices. We'll investigate eigenvalues and eigenvectors of those types. These 2 types of matrices show up very often in application and set the foundation for most of the advanced theory, assuming special structure in matrices. Once we have this under our belt, we're going to take a look at minimization principles and how to interpret eigenvalues geometrically using the concept of minimization. We saw that in least squares, and we're going to develop an analogous approach in eigenvalue theory. The last part of our introduction will be to cover the idea of incomplete matrices. These are theoretically very important, though in practice, incomplete matrices form a very small subset of the larger type of problems that we want to solve. They're worth mentioning so that we're not surprised if we trip over one. However, the main thrust is going to be to prepare us to apply eigenvalue theory in the context that we are most likely to see them, which are these other major ideas. At the end of this process, we're going to actually leverage the intuition that we build to fully solve the couple pendula problem and complete the mathematical modeling process for the standard eigenvalue problem that arises in that case. Because I recognize that the introductory work actually are prerequisites for more advanced theory, let's give a brief overview of the advanced levels of eigenvalue education. One of the first things that I would recommend students to do is to go hunt down and train themselves on how to apply eigenvalue theory in more advanced context. This will require insights into the type of classes that teach that and the type of interdisciplinary knowledge that relies on that information. Office hours are a great way to get that, as well as online searches. At this point, there's some really good online searches of people who have asked those questions that you can find for yourself. once we have access to meaningful, large eigenvalue problems, one of the first things that comes up is how do we compute those things if we're not going to do it by hand? That's what I would call numerical linear algebra. It's a very, very popular field and quite powerful. And in order to do that, we would use specialized eigenvalue software libraries. For those of you that want to learn more about that, I would definitely recommend that you take Introduction to Numerical Analysis, and perhaps that's a 3-sequence class. Later in my career, I plan to do a sequence of videos. Each lesson is designed to introduce a specific algorithmic approach to computing eigenvalue problems. There are kind of 3 very popular algorithms. One of them is called the power iteration. Another one is called QR-based algorithms that take advantage of similarity transformations to transform an original matrix into a simplified form, very similar to what we did in Gaussian elimination, except with orthogonal matrices on the left and right-hand side. And then finally, there's an approach called tri-diagonalization, where we turn our original matrix A into a tri-diagonal matrix and then apply special matrices to find the eigenvalues of that one. There are also more advanced algorithms that take advantage of some of these foundations and apply preconditioners, blah, 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 blah. At this point, I do want to give a shout out to a resource that is quite useful to get insights into specialized eigenvalue software libraries, as well as customized algorithm to solve very large scale eigenvalue problems. If you go to any search browser and type in templates for the solutions to eigenvalue problems, you'll get a result at the top, which is a book from SIAM, Society of Industrial and Applied Mathematics. Up here, this is the website of a man named Zhaozheng Bai. He's one of the editors of this book. If you read this, you're welcome to do that on your own. You'll get a sense of what this book is about. It's designed for practicing engineers and mathematicians who need to solve eigenvalue problems and want to find algorithms to do that. What's crazy about this book is that the entire contents are available online in HTML format. So you can get access to this. If you buy it on Amazon, it's about $100, but this gives insights into the more advanced levels of eigenvalue theory. And it also hopefully will motivate you to take the introductory material much more seriously, because once you get the introduction under your belt, a lot of the theory that is covered in these more advanced techniques, you'll be ready to understand the foundations. With that, we're ready to start our work building intuition in the case of small eigenvalue problems involving 2x2 matrix. That's exactly what we're going to do in the next videos.